Okay. Let's start part 2. We are considering Lagrangian submanifold in Kähler manifold. N omega J G is a Kähler. L is n-dimensional Lagrangian submanifold. The Lagrangian submanifold is homogeneous. Lagrangian submanifold is called homogeneous, and if this Lagrangian submanifold is obtained as orbit of subgroup for some D subgroup, connected D subgroup of the automorphism group of Kähler manifold. This group consists of diffeomorphism of M, preserving Kähler structure, preserving omega J G. J is a complex structure. G is Kähler metric of. Such Lagrangian, and we called such Lagrangian submanifold is homogeneous Lagrangian submanifold. And so we recall yesterday's my lecture. I mentioned the result, and the compact, if the homogeneous Lagrangian submanifold is compact, then and it is always Hamiltonian minimal, H minimal. Hamiltonian minimals. Namely, and the first variation of volume under every Hamiltonian deformation of given Lagrangian submanifold vanishes. Delta. This is Hamilton minimal Lagrangian equations. Alpha H denotes the so-called mean curvature form, namely one form corresponding to the mean curvature vector field. This H means mean curvature vector field. This H means Hamiltonian. Please don't confuse. This observation is very easy, very elementary, by using divergence formula on compact Lagrangian submanifold. Okay. And yesterday I explained Hamiltonian minimality and Hamiltonian stability problem and result in the ambient Kähler manifold complex Euclidean space and complex projective spaces. And first I want to make a related remark here. And previously, more than 25 years ago, and this and Urbano and independently I showed following result ですね。a little bit modified statement. We assume and Kähler manifold, ambient Kähler manifold is complex space home. Complex space home. Complex space home means Kähler manifold with constant holomorphic sectional curvature. The complex space home is locally isometric to complex Euclidean space and complex projective space with Fubini study metric and or complex hyperbolic space. And we assume L is compact Lagrangian submanifold. Compact Lagrangian submanifold in complex space home. If Lagrangian submanifold is Hamiltonian minimal and non-negative sectional curvature. Non-negative sectional curvature. And then L has parallel second fundamental form. L has parallel second, satisfy this equation. S denotes the three symmetric three tensor field defined by the second fundamental form of the submanifold L. Okay. Then such Lagrangian submanifold, as I mentioned yesterday, such Lagrangian submanifold with parallel second fundamental form were already classified by Lie theory and by symmetric R space theories. And about the beginning of 1980, Professor Hiro Ohnita and Masaru Takeuchi gave complete classification theory of all Lagrangian submanifold with parallel second fundamental form. Please note that this condition implies Hamiltonian minimal. Alpha H is parallel. It should be alpha H mean curvature form must be parallel. And they classified such Lagrangian submanifold in complex space forms. Okay. Okay. And according to this classification, we can know such Lagrangian submanifold, such explicitly, concretely. So, from this result, we know compact Lagrangian submanifold in complex space form and Hamiltonian minimal. Hamiltonian minimal compact compact Lagrangian submanifold in complex space form with non-parallel second fundamental form must have it does not have non-negative sectional curvature. There exists negative sectional curvature. And combining this result, the compact homogeneous Lagrangian submanifold in complex space form must be Hamiltonian minimal. If such Lagrangian submanifold, if the MNC compact, this is compact Lagrangian submanifold, homogeneous Lagrangian submanifold. And if second fundamental, of course, non-parallel. Such homogeneous compact Lagrangian submanifold is H minimal, Hamiltonian minimal, by this proportion. And combine and from this theorem, compact homogeneous Lagrangian submanifold with non-parallel second fundamental form. This Lagrangian submanifold has negative sectional negative curvature for some sections. Okay. Such case, the Lagrangian submanifold has induced invariant metric and without non-negative sectional curvature. Remark. Then this result, and if we take ambient, if you take as ambient Kähler manifold and Hermitian symmetric space of rank greater than 1. For example, complex hyperquadratic. The complex, and later I shall explain the more precise descriptions. The complex hyperquadratic. This is Hermitian compact type Hermitian symmetric space of rank 2. In this case, the QNC and compact homogeneous Lagrangian submanifold and with not second fundamental form parallel, not parallel, however with non-negative sectional curvature. If you ambient manifold is not complex space form, higher rank Hermitian symmetric space, we find such Lagrangian submanifold. This statement does not hold for Lagrangian submanifold in not complex space. We can find even in the case n equals 3. Later such example we can show concretely. So for Hamiltonian stability for complex Lagrangian submanifold with parallel second fundamental form, we show the following result. This is an extension of result of my PhD student Amaruzaya. For any compact embedded Lagrangian submanifold with parallel second fundamental form must be Hamiltonian stable in the sense of second variation volume non-negative under every Hamiltonian deformation. Okay. Next, I want to mention example of Hamiltonian stable minimal Lagrangian submanifold with non-parallel second fundamental form. First I thought Hamiltonian stability implies parallel second fundamental properties. However, I myself was able to find counter examples, or independently Beduri-Gori found the same counter examples. Such Hamiltonian stable minimal Lagrangian submanifold is given by using the representation of SU2. The irreducible unitary representation of SU2 are well known, very elementary classified. we use irreducible unitary representation of SU2 and of degree 3. Degree 3 means the representation space is a vector space of all complex homogeneous polynomials with respect to G0, G1. These are two variables of degree 3. This is a four-dimensional complex Euclidean space. The SU2 naturally acts in V3. The V3 can be identified with the three symmetric product of C2. C2. We take an orbit of SU2 through this point. G0 3 powers plus G1 3 powers plus this element. This is the element of V3. We take a point representing to this. If you take an orbit of this point, it becomes three-dimensional compact embedded minimal Lagrangian submanifold. By using momentum maps, why the orbit of this element become Lagrangians? We can know by using momentum map argument. Then by calculation of second variation, using Peter Wild's theorem and harmonic analysis on SU2, direct computation, we showed strictly Hamiltonian stability of these examples. This is the first example of Hamiltonian stable minimal Lagrangian orbit and with non-parallel second fundamental on the three-dimensional. I omit other differential geometric curvature property of these examples. It was discussed by Ban and Chen and Blanken and other authors. I must mention Beduri and Gori gave more examples, many examples. Minimal Lagrangian, homogeneous minimal Lagrangian submanifold in complex projective space. They classified compact homogeneous Lagrangian submanifold in complex projective space obtained as orbit of compact simple Lie groups of SUN plus 1. SUN plus 1 is an automorphism group of Kähler manifold CPN. Essentially they used pre-homogeneous vector space, classification theory of pre-homogeneous vector spaces due to Professor Mikio Sato and Tatsuo Kimura. Mikio Sato is a famous Japanese mathematician, soliton theory. They gave 16 according to their classification, 16 examples of minimal Lagrangian orbit in CPN.
Dimension K is smaller than n plus 1.
K, dimension.
K is smaller than n. K, simply K means the orbit of K.
K. Yeah, K.
K is smaller than 1n.
K is a subgroup of SUN plus 1. K.
Lagrangian means the dimension K is
K orbit.
K must be n, right?
Orbit. The dimension of orbit of K is n. Yeah. Orbit. The dimension of orbit is K. N. Sorry. N. Yeah. They classified the Lagrangian orbit and the corresponding representations. They give a nice list of 16 examples of minimal Lagrangian orbit. The five example with parallel second fundamental form are contained. We are familiar with these examples. Naito Takeuchi's examples. Obviously, such example contains
What's the meaning of the pre-homogeneous vector space?
pre-homogeneous vector space. Yeah. This is this is a complex vector space, and the GLV, and G, if G and V is a representation space of the D group group G. The G has and Zariski open orbit. Zariski open G open orbit. And typical examples C. Okay, C. Multiplication. The orbit is C0. Saturate. The BQ sort of classified. They give complete classification of such representation, such irreducible representations. Yesterday I mentioned and sorry. Based on this observation, sorry. No. This one. Yesterday I mentioned these observations. Existence of Lagrangian orbit is equivalent to existence of complexified Stein orbit. Based on the Sato Mikio and Kimura Tatsuo's work, the Beduri and Gori determined all representation of with Stein-Zariski open orbit. A case-by-case treatment. It should be hard work. Sorry. It should be hard work. Okay. Of course, they classified Lagrangian orbit of compact simple Lie groups. And of course, the classification of Lagrangian orbit of non-simple, semi-simple compact Lie groups. They're still open problem. Very recently, Podesta sent me a new result. Their new result. They showed this is a non-simple case, non-simple, semi-simple Lie groups. This is a 5-dimensional minimal Lagrangian orbit of this is a product of SU2, the non-simple, semi-simple compact Lie groups. There are such examples. And they showed Hamiltonian stability of these examples. Okay. However, there are so many open problems. Okay. And I want to give remark to two questions. In the sense that I cannot find any counter example to the question of conjectures. It's hard to determine the Hamiltonian stability of given compact minimal Lagrangian submanifold. My question, is it true that any compact embeddedness is important? Embedded minimal Lagrangian submanifold is always Hamiltonian stable. Or I think this is too optimistic. Or is there compact Hamiltonian unstable minimal Lagrangian submanifold embedded in CPM? No, I think I do not know any counter examples. And in the case complex Euclidean space, similar questions. I want to give similar questions. Any compact embedded Hamiltonian minimal Lagrangian submanifold in complex Euclidean space, Hamiltonian stable. Or no, or is there unstable example in Cn plus 1? ですね。そう。で、known example, I checked ですね。Hamiltonian stable. Okay. The next, how about Lagrangian submanifold, nice Lagrangian submanifold in compact irreducible Hermitian symmetric space of rank greater than 1. Okay. Most beautiful example of Lagrangian submanifold in compact Hermitian symmetric space should be real form. And Professor Makiko Tanaka discussed very nice lecture, nice result ですね。On real forms of compact Hermitian symmetric space. The real form is a fixed point, connected component fixed point set by anti-holomorphic isometry of ambient Hermitian symmetric space. Due to Professor Masaru Takeuchi's work, such objects are equivalent to L must be canonically embedded symmetrical space in Hermitian symmetric space, and it must be a totally geodesic Lagrangian submanifold. And any totally geodesic Lagrangian submanifold can be obtained as canonically embedded symmetrical space, and it should be real forms. Professor Masaru Takeuchi showed converse. It gives a very nice class of Lagrangian submanifold in compact Hermitian symmetric space. How about Hamiltonian stability? Hamiltonian stability of such real form. Based on Masaru Takeuchi's use, and we discuss details. Hamiltonian stability for real form in Hermitian symmetric space. The real form, we can give concrete and complete list of real form in Hermitian symmetric space. Then we can find three types of example of Hamiltonian unstable Lagrangian submanifold. Though real form is a very nice, very beautiful Lagrangian submanifold. However, there are Hamiltonian unstable Lagrangian submanifold. They exist. The three cases. This is a pair of this is Lagrangian real form in ambient Hermitian symmetric space. The first one is a real form in complex hyperquadric. The second one is this is the Lagrangian submanifold in this Hermitian symmetric space. And classical type. Then this is a real form Lagrangian submanifold in exceptional Hermitian symmetric space. These examples are Hamiltonian unstable examples. I must mention Professor Makiko Tanaka's work and her colleagues, Irie Sakai Takashi. They studied using real form of compact Hermitian symmetric space. They discussed tightness program and intersection theory and Lagrangian intersection flow homology problem for in that case it's very detailed, beautiful theories. Okay, this is the totally geodesic case. How about the slightly more general case? How about non-totally geodesic Lagrangian submanifold in Hermitian symmetric space with parallel second fundamental form? This is nice condition. Non-totally geodesic Lagrangian. How about classification of non-totally geodesic Lagrangian submanifold in Hermitian symmetric space with parallel second fundamental form. The such Lagrangian submanifold were already classified. Result due to Professor Jürgen Berndt, Eschenberg, Hiro Ohnita, and Kazumitsu Kada. ね。で、they classified wider class of nice submanifold ですね。They complete classification of extrinsic symmetric submanifold in Riemannian symmetric spaces ですね。で、this classification implies a classification of such Lagrangian submanifold ですね。で、from this classification we can find one canonical one parameter family of Lagrangian submanifold with parallel second fundamental form ですね。including only one totally geodesic Lagrangian in that case, in these cases ですね。Of course, in this case, I do not know the Hamiltonian stability. They are Hamiltonian stability ですね。This is non-totally geodesic case. Okay. Next, we shall concentrate the ambient Kähler manifold. Ambient Kähler manifold is complex hyperchadric, which is compact Hermitian symmetric space of rank 2. It is also an interesting problem to investigate Lagrangian submanifold geometry in individual Hermitian symmetric space using the proper geometric structure of its own geometric structure of each Hermitian symmetric spaces. We shall concentrate Lagrangian submanifold geometry in complex hyperchadric. What is complex hyperchadric? Complex hyperchadric is a complex algebraic hypersurface in n plus one dimensional complex projective space defined by homogeneous quadratic equation. This equation. G0 square plus dot Gn plus 1. Very nice equation. The first Riemannian geometric observation, this complex hyperchadric can be identified as a real Grassmann manifold of oriented to planes. We denote by these notations. Rn we consider n plus two dimensional Euclidean space, real Euclidean space. And the W is a oriented two-dimensional vector space of n plus two-dimensional Euclidean space. The bracket means that we fix the orientation of two-dimensional vector subspace of W. The bracket W means unoriented two-dimensional vector subspace of Rn. This consideration of orientation is very important. Very important. We consider the set of all oriented two-dimensional vector subspace of n plus two-dimensional Euclidean space. This is a Grassmannian manifold. Grassmann manifold. This Grassmannian manifold can be naturally embedded in the vector space. Two exterior product of Rn plus 2. We have natural. This is so-called Prica embedding. The identification between QNC and this real Grassmannian is given as follows. The W bracket denotes the oriented two-dimensional vector subspace. You take the bold AB, also normal basis of this oriented two-dimensional vector subspace. They are compatible with its orientation. Very natural basis of this. And by using this basic, you take complex vector A plus root minus 1 times B. This is a complex vector in Cn plus 2. This vector defines a point in QNC. Easier to check, to be checked. We can define. This means complex hyperchadric can be treated as a Grassmannian geometry ですね。Grassmannian geometry ですね。で、complex hyperquadratic and oriented to plane Grassmannian and homogeneous SON plus 2 over SO2 times SO0 ですね。They are same ですね。same. Okay? And sorry. This is a joint work with Huimars. Okay. We are studying Lagrangian submanifold geometry, complex hyperquadratic. We did our result. We did and construction of nice class of certain compact minimal Lagrangian submanifold in complex hyperquadratic, and by the gas map of from isoparametric hypersurface in the unit spheres. The results here. Sorry, please. Previous one. Okay. Yeah. Oriented to plane. Oriented.
Grassmannian 2 tilde Rn plus 2. Those are equal to QNC or?
Yes, equal to QNC. Can be identified in this sense.
Double intersection equal to 0. So not open set. Not open set QNC. It's equal to open set of complex.
Equal to open set? QNC is that?
Equal to
identify. Okay. This is called different isometry, different words. You can not open set. Such a glass map construction of Lagrangian submanifold in complex hyperquadratic, it was mentioned at the talk of Professor last talk. We discussed the property of so obtained Lagrangian minimal Lagrangian submanifold in complex hyperquadratic. One of the main results, we gave a complete classification of all compact homogeneous Lagrangian submanifold. We classified all compact homogeneous Lagrangian submanifold obtained as a compact Lie group of SON plus 2. SON plus 2. SON plus 2. We don't assume the simpleness of compact Lie groups. Any compact. Then we investigated the Hamiltonian stability property, and more precisely, strictly Hamiltonian stability property. We determined such compact embedded minimal Lagrangian homogeneous case. We determined. All compact homogeneous minimal. We determined strictly Hamiltonian stability of all compact homogeneous minimal Lagrangian submanifold in complex hyperquadratic. We determined. We succeeded in determining. We spent several years. Okay. First, I want to mention how to obtain such a class of minimal Lagrangian submanifold. Okay. The Lagrangian submanifold geometry in complex hyperquadratic has nice relation with hypersurface geometry in complex hypersurface geometry in complex. The Lagrangian submanifold geometry and hypersurface geometry in n plus 1 dimensional unit standard spheres. and this is not precise bijective correspondence. There's some connection, links, corresponding. Yeah, I shall explain. I shall explain, and so. The first, we assume Mn is a n-oriented hypersurface in n plus one dimensional unit spheres. And the bold X denotes a position vector of hypersurface, and the bold N denotes a unit normal vector field and oriented hypersurface Mn in Sn plus 1. Yeah. Sorry. And this is a n plus 1 dimensional sphere, and in n plus 2 dimensional Euclidean space, and this is the origin. Then now we give to hypersurface Mn. Then the bold X, we take any point. This is P, small p is any point in Mn. Then we take position vector of P. Position vector means this vector. This is a position vector. This is xp. This is a position vector. Then we take the unit normal vector. Unit normal vector np. And np is a normal to hypersurface Mn and tangent to sphere, tangent to n plus 1 dimensional sphere, like this. Okay. The vector np, xp and np is both are unit lengths, and xp and xp is perpendicular to np's. The xp and np are also normal. You can take and oriented two-dimensional vector subspace spanned by xp and np. They're like this. You take oriented two planes. Oriented two planes. Oriented to two planes. Then we define orientation on these two planes. They are determined by vector xp and np. This oriented to two plane, we call this oriented to two plane. We call this xp, gp. Sorry, gp. Capital script GP. This oriented to two plane and defines a point in QMC. Identified with oriented to two plane Grassmann. Each P. This oriented to two plane and defined from arbitrarily given point P. Then we have this point corresponds to xp. We have mapped to Mn to QNC. We have mapped to QNC. This is G. We denote by this map, G, script G. QA だし。This is an observation, very classical observation. This map is always smooth immersion and Lagrangian immersion, relative to standard Kähler structure, standard Hermitian symmetric structures, Lagrangian. This means any oriented hypersurface in unit standard sphere gives a Lagrangian submanifold, immersed Lagrangian submanifold in QLC, immersed in general. And we can observe the deformation of oriented hypersurface gives a small Hamiltonian deformation. Any small Hamiltonian observation can be obtained as small deformation of original hypersurface. Nice relations. Then of course, we can explain this construction from the viewpoint of Einstein-Sasaki contact geometries, isometries. Then so this is Lagrangian immersion. Without singularity. And the mean curvature, we are interested in mean curvature form of this Lagrangian immersion. The Bennett Parra to describe the mean curvature form in terms of principal curvature of original hypersurface, like this. This case. Okay. The professor they discuss the details, the property of this formula, and they construct new examples. Okay. Then from this formula, if we assume principal curvature, all principal curvature are constant. They automatically, this is constant alpha h equals 0 ですね。very elementary ですね。principal curvature of original hypersurface constant. Implied this is alpha h equal must be 0. G is minimal Lagrangian immersion. If you take Mn, if you take as Mn, oriented hypersurface with constant principal curvatures in unit standard sphere, you obtain an example of minimal Lagrangian immersions. Okay? Then we assume constant principal curvature. Study of such hypersurface has long history since Eric Cartan's. You also mentioned the so-called isoparametric hypersurface. Such hypersurface is given by level hypersurface and for isoparametric functions. There's a long history. Still interesting, very interesting subject. Many geometers are studied. We assume the classification theory classification almost classified at the present. So and we assume isoparametric hypersurface. We assume Mn is isoparametric, compact isoparametric hypersurface. This is embedded hypersurface in unit spheres. And you take a gas map. We can show not only this gas map is minimal Lagrangian, the image, but also image of gas map is a smooth embedded submanifold. The gas map gives covering map with deck transformation ZG. Small g means the number of distinct principal curvature of Mn. And M1, M2 denotes the corresponding multiplicity of principal curvatures. and every Cartan-Newton's gives a very important result and surprising result ですね。Okay, ちょっと briefly ですね。This is a fundamental theory ですね。で、Newton's surprising result ですね。Newton's G must be 1, 2, 3, 4, 6 ね。で G イコール6ケース M1 イコール M2 ですね。G で and イコール1は2 the average result で、isoparametric hypersurface is given by the level set of polynomial function satisfying this partial differential equations, so-called Cartan-Newton equations. Okay. This is a classification result. All isoparametric hypersurfaces are classified homogeneous one and non-homogeneous ones. They're almost classified. Still, and a matter of time, I think. And homogeneous one I think Jürgen Bent mentioned this result. Homogeneous isoparametric hypersurface obtained maximal dimensional orbit, principal orbit of isotropy representation, rank 2 symmetric space. Each case are described. The non-homogeneous one exists, discovered first by Professor Hideki Ozeki and Masaru Takeuchi, and generalized by Felius Calcula Münzer by using Clifford algebra constructions. The recent big progress, classification of G equals 4 cases. Now, roughly speaking, homogeneous isoparametric hypersurface is constructed from isotropy representation of Riemannian symmetric space. The another one, the non-homogeneous one, are constructed from Clifford algebra construction, Clifford systems. This is there is some relation of isoparametric hypersurface with integrable systems. Ferapont mentioned. That's another direction. By using this theory, I want to mention general remark of I mentioned the image of Gauss map. This is image of Gauss. We assume M is isoparametric hypersurface. Image of Gauss map. This is smooth embedded minimal Lagrangian submanifold. Compact embedded minimal Lagrangian submanifold. This is the GZ covering. We can describe explicitly the group action of a finite cyclic group of order G on isoparametric hypersurface. This actually is not isometric. This is Lagrangian, n-dimensional Lagrangian submanifold. We are interested in this object. And we can observe the homogeneity of original isoparametric hypersurface equivalent to the homogeneity of this Lagrangian submanifold. We observed this in our joint paper with free mass. So, this means if we take non-homogeneous isoparametric hypersurface, then we obtain non-homogeneous compact minimal Lagrangian submanifold embedded in QNC. The non-homogeneous, however, it should be nice Lagrangian submanifold, nice non-homogeneous Lagrangian submanifold, I think. Then more property of such Lagrangian submanifold in the sense of symplectic topology. This should be monotone and cyclic, and whose minimal Maslov number is equal to 2n over g. 2n over g. This is a distinct number. This is a very fundamental invariant, Hamiltonian invariant. Invariant. Okay. The homogeneity. Yeah. This is a classification. This is classification theory, classification result of this is an argument of classification. So, the classification result of compact homogeneous Lagrangian submanifold in QLC, our result. We assume L is a homogeneous, compact homogeneous Lagrangian submanifold obtained as a compact Lie subgroup of SON plus 2. SON plus 2 is an isometric automorphism group of QNC. We assume L is a compact homogeneous Lagrangian submanifold of G, such G. In this case, there is a homogeneous isoparametric hypersphere. We can show homogeneous isoparametric hypersphere from this assumption. Its Gauss image of Gauss map. Its image of Gauss map. In general, the image of Gauss map does not coincide with the original homogeneous Lagrangian submanifold. This is first, the two cases happens. The first one is the Gauss image of Gauss map of this homogeneous hypersurface coincides with given compact Lagrangian, compact homogeneous Lagrangian submanifold. Given compact homogeneous Lagrangian submanifold coincides with the image of homogeneous isoparametric hypersurface. This is first case. The second case. Second case. If not, we can show if not, L. We can show L belongs to a certain Lagrangian deformation of Gauss image of homogeneous isoparametric hypersurface. We can give such Lagrangian deformation explicitly. The case B, second case can happen. The second can happen four type. From case 1 to case 3, the corresponding Lagrangian submanifold is parallel second fundamental. We found 4 cases. This is a fourth case gives a new example of one parameter family of homogeneous Lagrangian submanifold with non-parallel second fundamental forms. So, I shall skip. Finally, I shall mention the Hamiltonian stability result of image of Gauss map. I must remark the Hamiltonian stability of Gauss map itself is an easier problem. The Gauss map is Hamiltonian stable if and only if the original isoparametric hypersurface great spheres. Gauss map is embedding case. This is the easier case. The Hamiltonian stability property is a global property of the submanifold. Our problem is that determines the Hamiltonian stability of image of Gauss map. We succeeded to determine the Hamiltonian stability of Gauss image, all homogeneous isoparametric hypersurface. technique is a very classical harmonic analysis on compact homogeneous space, case by case. で、そうそう。で、G イコール1 and 2 casesは、ガウスイメージでトータリジオデシックケース。で、in this case は、ハミルトニアンスタビリティプログラム G イコール1 and G イコール2 case and reduced to that Hamiltonian stability result of real form. In this case はリアルフォームですね。で、G イコール3 and G イコール4 and G イコール6 case. ガウスイメージ is not totally geodesic. This is not totally geodesic. Not totally geodesic. The if and only if G equal 3, 4, 6. Then in this case we obtain the non-totally geodesic minimal Lagrangian examples. The first, the G equals 3 cases. Our result G equals 3 cases. The strictly Hamiltonian stable we showed. The next, we showed G equals 6 cases. Two homogeneous examples. They are strictly Hamiltonian stable. I must remark, G equals 2 cases can happen Hamiltonian unstable examples. Hamiltonian unstable, G equals 2 cases, we have Hamiltonian unstable example. The difference of multiplicity of principal curvature is greater than or equal to 3. The Gauss image is Hamiltonian unstable. However, this example are contained in the Hamiltonian stability result of real form in Hermitian symmetric space. I already mentioned this case, real form. Finally, after G equals 3 and G equals 6 work, we studied G equals 4 case, most complicated cases. The case by case we treated. Then we found G equals 4 case, we found unstable examples. There are G equals 4 case, G equals 4 case, 6 types, 6 third example, fourth example, fifth example. This is an infinite series of isoparametric, homogeneous isoparametric hypersurface with G equals 4 case. And at the same time, example 3, 4, 6 are OTFKM type. Homogeneous and OTFKM type. In this case, we found the result. The difference of multiplicity is greater than or equal to 3. The Gauss image is not Hamiltonian stable. Common properties, common Hamiltonian unstable property. We observed. The case by case. Then the final case in G equals 4. This is exceptional case. We spend most efforts to determine. In this case, the difference of multiplicity M1 minus M2 equals 3. First, we conjecture this example. This case is a Hamiltonian unstable. However, after very careful discussion and computation, we conclude this case is strictly Hamiltonian stable. We can summarize the conclusion like this. There are other related this Lagrangian submanifold construction from isoparametric surface is related to construction of cohomogeneity one special Lagrangian submanifold in tangent bundle over standard spheres relative to stencil metric, complete rich flat Kähler metric on tangent bundles. Some related work by given the Takashi Sakai and PhD student of OCU, Kaname Hashimoto, wrote this paper to appear in Tohoku Mathematical Journal. And extension to semi-Riemannian case recently, and I'm discussing with my new PhD student on the. In this case, it should be related to J. Hahn's work. and semi-Riemannian isoparametric hyper surface works. Okay, so, several further programs. Further programs studies non-homogeneous case, Hamiltonian stability and the property of non-Gauss map, Gauss image of non-homogeneous case, non-homogeneous isoparametric hyper surface. And so, and third problem is a study of classification and the classification of the property of Lagrangian submanifold in other Hermitian symmetric space. Other Grassmannian manifold. Lagrangian submanifold, Grassmannian manifold, Lagrangian submanifold in two-plane complex Grassmann manifold. Two-plane complex. Next very interesting problem, I think. Thank you. Thank you for attention.
Thank you for your